So hi everyone, thanks Tali for organizing this wonderful meeting. Oh, is this the clicker? I'll just do it from here. No.
You need to press the lower.
This one.
Right here.
No, but for switching.
Alright, if it's not connected, it's not going to switch.
Okay. Anyway.
Need the other part.
Oh, the USB. Does someone have it? Does someone
I
have
don't know
it?
if this was ever used, but you can use mine.
Okay.
Take a second. I never trust these things to last me.
Okay. Anyway.
Press
Oh, wrong top.
play.
Yeah, no, it's different talk. Okay. All right. I have a 5-minute version of this talk, so I'll just adapt. Okay. So machine learning is much about learning mappings between inputs and desirable outputs, say speech and what was said, text and its translation, images and what's in the image, tissues and their condition, etc. And over the last 5 to 10 years, we've seen tremendous growth in the accuracy, improvement in the accuracy of these systems, with many success stories like image classification or categorization. So say what's in this image, it's a quail. Speech recognition, face recognition, etc. Really a drastic improvement in accuracy. And all these systems and many others use basically similar fundamental ideas, which I'll describe in this classical paradigm slide. So this is ML 101. So how do you build such systems? You take labeled data, a lot of labeled data. So labeled data, I mean images and a description of what's in the image. Say if you want to build an image categorization engine. Then you turn the data into features, numbers, say the gray levels or RGBs in the image. Let's call the features X and the labels Y. And then you search for, you try to learn a function that maps from X to Y, and this function has some parameters, and parameters W, and you try to find W that works well on the training data. So that's basically learning as it's working today. And there's obviously a lot under the hood here. So one caveat is to get these systems to work well, you need a lot of data, a lot of labeled data. And that's often hard to generate, especially if you don't have resources like the very large companies. And in some cases requires expertise, for example, in natural language processing problems. To parse sentences, it requires expertise on the part of the annotators. On the other hand, unlabeled data, that is, say in the example of images, just images without someone telling you what's in the image, that's practically unbounded, right? There are billions of images on the web. So, it's a major challenge of machine learning nowadays to be able to improve algorithms by using this unlabeled data. Okay? So here's a simple strategy that will be the starting point of what we'll discuss. It's called self-training. Basically says, you have a training, an algorithm that can use labeled data. Just train it on whatever data you have. And now you have a lot of unlabeled data. Label that data with your model, and then retrain. Okay, so that's often called self-training. It's not as silly as it sounds, at least not in practice. It sometimes works fairly well if you sort of hack it enough. So here's the scheme again. Let's say you have labeled data. You train a model on that. Now you have a model. Now you have a lot of unlabeled data. You take your model, you apply it to the unlabeled data, and your model says that this is corn, this is apple, and it thinks this is a rainbow, okay? So that's the danger, right? You apply your imperfect model to data, and it's going to make some mistakes. And now if you retrain, or you try to train using this relabeled data, you'll be using something that's wrong, okay? So, and this error might propagate, causing your model to actually become worse. Okay, so assigning labels and then reusing them is dangerous, right? Because you might get it wrong. So one of the major goals of this work is to think about assigning confidence labels. Okay, so being able to avoid this case where we somehow assign a wrong label and somehow having our relabeling mechanism be aware that this is not a label that we should give. Okay, so it would be nice, and all of this would work perfectly if we could just use only perfect labels. Maybe some of the labels we can't assign, but then at least we don't make mistakes. Okay, so this comes back to this major theme that we've also heard about in this conference, also in Daniel Wolpert's talk and others, is this notion of confidence, right? For us humans, you know, in cognition, it's an important notion, basing our decisions on confidence and evaluating confidence. And it turns out, if you want to do this properly, if you want to have some measure of confidence that's correct in some sense, that's a tricky thing to come up with, and I'll propose something that I think makes sense. Okay, so again, our goal is going to be to come up with some notion of confidence that we can use in schemes like that. So if we say a label is, say, apple, we want to be sure that it's really an apple. Okay, so how do we do that? So just another word about self-training. It has become a very popular approach, say, in natural language processing. It works fairly well, but it can be improved substantially, I think. It's particularly important in deep learning because deep learning algorithms are really data hungry. Okay, they don't work if you don't give them a zillion data points, and it turns out that it's better to give them a lot of labeled data that might not be perfect than not giving them labeled data at all, or giving them not enough labeled data. Okay, so this is this issue of assigning or labeling unlabeled data is especially important in this context. And then, confidence is an issue in that case. Okay, so what I want to propose here, it's been done in various contexts, but I like to call it safe training instead of self-training, in the sense that you only want to assign labels where you think, and you have some good reason to believe that your labels are safe, in the sense that you're very confident about what they are. Okay. So how would that work? You have some labeled data, you train your model on the labeled data. Now you have unlabeled data, say these 3 images. Your model looks at these 3 images. For the first 2, it feels confident enough to say they're a corn and apple. For the third one, it says, I'm not sure. Okay? So I'm not confident enough to assign this label, and then I'm just not going to use this image in this round. Okay? And then you can use this relabeled data to train another model, and this other model might be now confident enough to say that this is an apple, or that this is Apple's logo. Okay. All right. So for example, if so these are examples you know about, but if I give you the sentence, I was schlimping yummy juice, okay? So you're not sure what schlimping is, right? But you have enough context and enough confidence in your inference abilities to say that schlimping is probably something like drinking, right? So you might be confident enough to say that this is, what this is, and then retrain. So if you encounter schlimping again, you can say that you know what it is. Okay. So how do we obtain a safe label? So let me just begin to formalize this. So we have some unlabeled data, say X, which is an image of an apple, and we want to be sufficiently sure that Y is an apple. So formally what we want to do is to obtain a good estimate of P of Y given X, P of the label given the image. And if it were the case that P of Y given apple given X equals this image is greater than some threshold, we'd be confident enough that this is indeed what's in the image, right? So if you could only have some reliable measure of this conditional probability, we'd be fine. We'd be safe. Yeah. Okay, so, but that's not as easy as it sounds, okay? So again, to formalize the problem further, so let's say we're given features, let's say we have n features, we're going to call them stars, the one that we observe. So we want to say something about this conditional distribution. So typically it's hard to estimate probabilities like that directly because you don't have enough, you don't see this combination of x1 to xn often enough to be able to estimate this probability directly, okay? Because you're going to need to, in order to properly evaluate this probability, you're going to need to see this apple, this exact image of an apple many times, and for someone to tell you that that's an apple, okay? But that rarely happens in these data sets. So you could use some models like logistic regression to train some conditional model, but there's nothing telling you that it's anywhere close to the real probability. Okay, so can we give a reliable estimate of these conditional probabilities? All right. So the answer is, as I'll show, that in some sense, yes, by using other things that we can reliably measure. Okay, here's how we're going to do this. The idea is that there are things that there are probabilities that are easy to evaluate or estimate from data. So for example, the probability of a label given just one feature, say xi, is easy to calculate, and you can get fairly reliable estimates on that. So just as an example, the probability that you will die if you fall from a steep cliff is close to 1, right? Okay, so you can evaluate these causes and effects. If you have like a single cause and a single effect, you can evaluate the probabilities pretty reliably. Okay, so let's say that this is the case, that you have the condition where the probability is 1. Now, here comes the first insight, that if I ask you now, what's the probability that y equals 1 given that x1 is 0, and then a bunch of other things happen, it's still 1, right? Okay? So it's like saying if you fall off a cliff, it doesn't matter if you wear a gray sweater or an orange sweater, you'll still die, right? But that's just because it's 1, actually. So, yeah, and that's guaranteed, right? But it might sound silly, but actually if the probability is 0.9 or even 0.99, then if you wear a green sweater, it might actually save you, right? You don't know. Because there might be some miraculous coordination between these conditions where that will change the condition probability. In the case that it's certain, then nothing can change it, okay? All right. Okay, so here's what we're going to do. We're going to assume that we have some simple reliable measurements in the form of these simple conditional probabilities. And we're going to use these to bound conditional probabilities. And we'd like these bounds to be provably true. Okay. So here's the setting. We assume we have n features. Let's assume they're discrete for this talk. And we have a label, a discrete label y. And there is some in the world, in the true world, there's some distribution, true distribution, binding these x's and this y, right? It's underlying the data. You never get to actually see it, but the data is generated from that. We don't know it. But we do often know some simple marginals of this distribution, like the probability of y given a single feature, the probability of y. And for the sake of this talk, we're going to assume that we actually know pairwise marginals. So the probability of pairs of features and the label. And I'll denote whatever we know by mu I j x I x j y. So someone gives you, these are actually easy to evaluate, to estimate from data, but let's assume that someone gives them to us and says they're true, okay? So you get a list of tables, pairwise marginal tables like this. Okay. And you get these for some set of pairs. It doesn't have to be all pairs. And we'll see that that's important, actually. Okay, so we get, say, mu 1, 2, mu 2, 3, and mu 2, 4. So pairs imply structure in the sense that you can plot 1, 2, 3, 4 and draw an edge between every pair of variables that appears in your pairwise marginals. So it turns out it's going to be important for our sake that this graph that describes the pairwise relations has no cycles, that it's what we call a tree graph. Okay, so some of our results are going to depend on that. So what's our goal now? Okay, this is our input. And our goal is to reason about the real distribution in the sense of answering queries about joint or conditional distribution. So I'd like to answer, say, what is this probability? Or what's this conditional probability? This is what we started out with, right? I want to know what's the probability that y equals apple given a certain image. Okay.
So mu I j are just the joint distributions?
Pairwise, yeah. Pairwise marginals for pairs of...
So y is binary?
Y is the label. You can, it doesn't have to be y.
So it's a joint distribution of all three of them?
Yes, that's right, yeah. But it's still less than n plus 1, right? Okay. So, and our goal is going to be, given some y star and x1 star to xn star, to say something about this conditional distribution. Okay. So, it's easy to see that this is the nail pose problem in the sense that it doesn't have, you can't answer, you can't give a number usually. Why is that? So this is what we know. We know these pairwise marginals, and we ask what's this conditional probability. So there's no exact answer because we only have partial information about the true distribution P. Right, so there are many distributions, P in this blue ellipse here that have these marginals, right? So we don't know what P is. We just know that it's in this big blue ball here. So let's denote by P of mu this set of all possible distributions that are consistent with what we know about P. So any point here is a distribution. And we want to know about this conditional distribution. So one point here might have, the value for this conditional might be 0.7, and in the other it might be 0.2, right? So there's a range of values that's consistent with our marginals. So what can we say about P1? It has a minimum value and it has a maximum value, right? That's fair to say. And the intuition here is that when the evidence for y is strong, so when our pairwise marginals convey that a given label is closely related to some features, we expect that this minimum conditional probability will be high. So if I tell you that the probability of y equals 1 given your x's is at least 0.95, you'll be pretty confident in labeling it with 1, right? So that's the idea. So we're going to look at minimum conditional distributions, and if these minimum conditional distributions are large, then we'll, this would be a good reason to actually believe this label. Okay.
This seems like a generalization of transportation.
It's actually, I mean, one formulation, this is similar to a flow problem, but, sorry? Okay, but your intuition is right that it's it's a linear program, essentially. I mean, it's, yeah, it's if you do it naively, it's a huge linear program, okay? And it's actually, I mean, it's a linear fractional problem, which you can turn into a linear problem. Okay, so the question is, can we calculate it, this minimum conditional distribution? And the answer is that in some cases we can, and in some cases we actually have closed form solutions for that as well. Okay, so this, what we did is to study bounds on this, well, we did a bunch of things. So we studied bounds on minimum and maximum joint and conditional probabilities. Again, we assume given pairwise marginals, and we can give results for minimum joint distribution, maximum joint distribution, and minimum conditional distribution, okay? In closed form in most cases. So the results are pretty easy to describe, so I'll do that. How am I on time? Okay, good. So I'll take it slow. All right. So here's the result for maximum probability. Okay, so I'll give the maximum, the minimum, and the conditional. So maximum joint probability. So we have these pairwise marginals. We assume that they conform to some tree structure. We denote by P of mu the set of distributions that are consistent with mu, and we ask for a given x1 to xn star and y star, what's the maximum probability for this assignment? Okay. Okay. So under all distributions that are consistent with our marginals, what's the maximum probability this event might happen? It's like saying in the most optimistic world for this assignment to the variables, what's their maximum probability? So the answer is pretty nice. It says that you need to minimize over all the edges and to find the edge with minimum probability for xi and xa star. Okay. So intuitively, it's like you said for a transport, right? This is what it is, right? So the probability has to flow through these marginals, okay? And this is sort of the lowest part that it has to flow through. So just to give you some intuition as to why this is an upper bound, showing that it's tight is a bit technical, so I won't go into all the details, but it's easy to see why it's an upper bound. So what are the pairwise marginals? What's a pairwise marginal? It says you need to sum over all the other variables, right? So the pairwise marginal for x1 and x2 is summing over all variables x3 to xn over all these assignments, right? So in particular, this sum is greater than any particular sum in here, right? And one sum in here is just x1 to xn star and y star, right? So from that we can conclude that the maximum over these probabilities is also less than any of these marginals, right? And that means that it's less than the minimum of these marginals, right? So this gives you the upper bound. And in fact, we can show that this is tight in the case of trees. So if your graph of dependencies is not a tree, then this is not necessarily tight. But if it is, then we can construct the maximum and we show that it's tight.
How is this related to something like maximum entropy?
So it's orthogonal to maximum entropy. Yeah, so this is going to imply least dependence, or the most dependence. Yeah, so it's going to push for maximum dependence instead of independence. So that's the price to pay for not assuming things, is that nature can be the most adversarial it can be. So the idea is, I mean, our intuition is that we're considering cases where these marginals do convey some information, and we want to capture, I mean, I don't need to convince you. We want to capture the essence of the information in there without making additional assumptions. And for us, it's very important not to make modeling assumptions because we want to use it somewhere where we don't want to believe any probabilities that a model makes. Okay, we want to have sort of real probabilities. Okay, so that was maximum probability. What about minimum probability? So again, we have an assignment x1 to xn. I dropped the y here just for convenience, and we're asking what's the minimum probability among all distributions that agree with what you know. What's the minimum probability of this event, x1 to xn star? So it turns out that it's this thing, where di is the degree of node I in this graph. Okay, so it tells you sum all the pairwise marginals and subtract the singleton marginals weighted by their degree. Okay, so it's and then make sure it's not negative. Okay, so this plus here just says clip it. If this came out negative, just clip it to 0. Okay, because probability shouldn't be negative. All right, so some intuition about this, or maybe non-intuition, but just to see what this does. So it's interesting that this will give you a probability eventually. And now you'll see that here you have sums of probabilities. And usually we're used to seeing in models, probability models, we're used to seeing probabilities multiply, right? So if you have an independent, like an IID model, then the probability of x1 to xn is going to be the product of px1, px2, px3, right? And here, they actually add up, which is funny because if they add up, they might add up to something that's greater than 1, potentially. But that doesn't happen, okay? Because we know it doesn't. So it's one interesting thing to notice. It's, as I told Tali, it's very different from independence. It actually sort of makes the opposite assumption of independence. Okay, and the case where this will be 1, where the minimum probability will be 1, is when there is a sort of provably deterministic relation between all the x's. So essentially when all the pairwise tables are deterministic and all point to the same assignment, then this minimum probability will be 1. So the proof is somewhat technical, but it has some interesting ideas. I'll just gloss very quickly over that. So you can turn this problem of minimum probability and turn it into first a linear program, and then we can take the convex dual of that. The dual variables turn out to be very similar to these pairwise tables that we had, but without any constraint of non-negativity or anything like that. Now, if you define lambda x1 to xn to be this function, then the dual is this thing. So it's again it's a linear program, but with an exponential number of constraints. And yeah, then we do some more massaging on this dual. I won't go into the details. We use something called the max marginal trick, which sort of reparameterizes this function lambda in a very convenient way. And then we can use that to show an upper bound and then tightness, and then get the closed form result. Right. So that was max probability, max joint probability, mean joint probability, and now our the goal that I started out with is conditional probability. So what's the minimum conditional probability? So this is tricky because it's a ratio of probabilities. What's conditional probability? It's a ratio of joint probability and marginal probability, right? So if you want to minimize that, that's no longer, at least immediately, a linear program, and you need to work some more. But it turns out that we can do that in closed form as well. So if you define this, so this is the function that we had before for the minimum joint distribution. So let's just define that to be f x and y. So it turns out the minimum conditional distribution is this ratio of f x star y star, which is the minimum probability, over the minimum probability plus something that looks like the maximum probability. So intuitively, you're sort of using the results that we had for minimum probability and maximum probability and taking their ratio. The fact that it works out is you need to work to show that, but it's true. Okay. Yeah. So far I assume that our graph of connections was a tree, but you can expand this to a non-tree case by considering sort of all spanning subtrees of a non-tree graph, which is something we can do for if you want to have margins that don't conform to a tree structure. So here's a simple example of just the min and max probability. So this is a 3-variable Ising model, and these are upper and lower bounds. So this is interaction strength. So this is where all variables tend to be the same. No, this should be, yeah, I guess it's for the other side. So this is where they all want to be the same and say 1, and this is where they all want to be different, and the extremes, our bounds are tight, and in the middle, as expected, there's some gap. Okay. So our next challenge was looking at the case where you want to predict not a single label, but a set of labels, which is something known as structured prediction in sort of machine learning terminology, and it has many applications. So for example, if you have this image, now you don't want to just say that there's an airplane in the image, you want to label each pixel. Okay, so your output is not just a single label, but a set of labels, one per pixel. Or you have a sentence, say this is your input, and your output is some parse tree. Okay, so your outputs are not a single label, but some set of labels or a more complex label. So this is known as structured prediction. So in that case, we might, since our y now is complex, it's not a single label, but it might be a bunch of labels, we might have input marginals like this that tell you something about the dependency between the y's. So the question is now, it becomes more complex. What can you say about the probability of a structured label given some input? So the good news is that we can find this minimum efficiently. We can write a linear program that does that. But we're very close to a closed form, and it actually looks more interesting than the single label case. It involves some flow, max flow type problem. So we're very close to proving that, but we're not there yet. Okay, so just to illustrate how this thing works, we consider this problem of part of speech tagging. So you have a sentence and you want to assign a part of speech to each word. And we use the pairwise statistics on word and word-to-word and word tag pairs. And we compared, so I won't go too much into the details, but we used some other probability estimate that's similar to a maximum entropy model. And we use that to sort of relabel the data. And we compare the accuracy of our model as a function of a threshold where you truncate the probabilities. And we see that this robust model based on these bounds does much better than the other model, because the intuition is that the probabilities calculated by these maximum entropy models are not to be trusted. Okay, they tend to be overconfident. These models. Okay. Okay. So to conclude, I hope I showed that it's possible to reason about conditional probabilities under some assumption, and to use this robust approach for considering all distributions consistent with your observations, and it yields non-trivial bounds that are sometimes available in closed forms and are, we think, empirically useful. And there are many other open questions, extensions, and applications. So, thank you.